Now that we've covered some of the theory behind 1D, 2D, and 3D approaches, I wanted to show an application to try to materialize these concepts. I want to take them out of the lab flume and off the classroom whiteboard and move them into the real geospatial world. Now, for reference, I've included links to some additional background materials, including this report, the bulk of which was written by HEC's Gary Brunner, and it includes some pretty extensive discussions on selecting an appropriate modeling approach to supplement what we've talked about already. Now, we've derived a few equations and presented some empirical alternatives in 1D, 2D, and 3D space. We've looked at some of the differences in terms of assumptions and limitations, but what does that mean to us today, right here where we sit? Here's a live face-to-face course. This one happens to show Chris Goodell teaching a class in Melbourne. Now, when I used to do live courses, which are hopefully returning again soon this year, one of the first things that we'll do when building a first hydraulic model together is to grab the terrain right where we're at and make the simplest model possible of the boardroom or the conference room, wherever we happen to be sitting. Now, we've already covered the GIS workshops about accessing terrain data and projects. There's no problem if we don't have the terrain data with us, though, because it's super easy to just make one from scratch, which is what we'll do momentarily. So typically, together as a class, we'll start by building a model of the room around us, and then we'll flood our virtual room. Because then I can point to the high water marks up on the wall. I can go around and mark out cross-section alignments with string. I can walk around to the different tables at different velocities that can be visualized. I can be the water particle for the discussion and then demonstrate reference frames to the observer, the attendees, in that way, and demonstrate other concepts like that in the room where it actually happens. And one of the things I'm going to try to do with any upcoming courses is to bring along a virtual reality headset that can take any flood that you can create and then use Google Earth or other tools to see the flood levels around you using those results that we export from our own tutorial models. There's some exciting applications like this that were featured in our technology webinar last December, and I'll provide a link to that as well. Now, this being an online course, we're a bit limited for using shared visualizations. This map here shows our flood modeling webinar registrations alone, and it shows the variety of places that you may be watching us from. So wherever you're joining us from around the world, I'll try to keep this next example simple enough where each of you could do this on your own. I'm coming to you, as you see here, from a small room that's packed full of some really nerdy stuff, but it probably wouldn't be very interesting to model in hydraulic software. So I thought I would go back to one of our earlier course locations and show you what we did there. Hopefully this location that I chose is a bit more interesting than the room I'm sitting in right now. It's from a few years ago. I did a course in New York City, and we could actually see the Empire State Building out the window. So I'm going to use that as my example here. You can see Central Park and a few other familiar landmarks: Carnegie Hall, Rockefeller Center, Radio City Music Hall, Times Square, and there's the Empire State Building. So let's zoom in on that. I've set up some saved views here, and we'll go to the Empire State Building itself, which you can see. Now, sitting in one of these boardrooms in our class, we could actually see the Empire State Building, including some of the terraces on the side, which I wasn't aware of before I went and toured it a couple years ago. So zooming into one of these terraces, let's go ahead and model this as if it's the classroom. So this might be a little more interesting than just a box room. And if I just delineate around the outside here, I'll need to pick an elevation. Now, I have terrain, but even if I didn't, I'm just going to create an empty terrain here. And this is just going to be a new terrain layer that's only what I assign here. So I'm going to call this the terrace. And I'll go ahead and add a new modification layer to it. In this case, it's a polygon, which I'll call this layer the terrace as well. And so as I draw around the outside of this, I'm going to take this polygon here, and I'm going to have to assign an elevation to it, which is going to override anything that I might have underneath it. In this case, it's its own terrain. So I'm not going to give it a name, but I will give it an elevation. We're about 30 floors up, so 100 meters. I'll call it even and say OK. So I've got this 100-meter high polygon. Now what? Let's go ahead and make a geometry. I'll start with 1D. So adding a new geometry here, I'll give it a name, 1D terrace, and we're going to bring some flow in one side and out the other. So I need a flow path. So starting with a river, I'm going to go ahead and draw that one in. And the river itself, I'm just going to go right down the center. Now this could be the center of a classroom if that's where we were sitting. In this case, I'm going to go right down the center of the terrace and delineate a flow direction. So I'll call this one terrace as well. I'm only going to have one reach, so I'll give it the same name. Only other thing I'm going to add to this is cross sections. I'm going to keep this as simple as I possibly can. I'll put in a couple of cross sections here, delineating from left to right, looking downstream, one at the upstream end, one right down the center here, and then I'll do another one at the end. See if I can get as close as possible to the end. Oh, that's one. Let me go ahead and move that over. I just want to get it to be 0. I'm at 39 there. I think the line is about 40 meters long. So I'll move that around a little bit. And again, it's numbered from downstream to upstream, but I've delineated it from upstream to downstream. So the river mouth at 0 is my chainage that way, my station, and I've got 0, 20, and 40. So these things are 20 meters apart. I'll save that geometry, and then we'll go back in and have a look at the geometry and see what it looks like with that 30-meter terrain, or that 100-meter high terrain surface and polygon underneath it. So when I open this up, let's see what we see here. There is the terrace, and I've got my 3 cross sections. Now they don't have any elevation. Each of these cross sections, they have elevation. They just don't have a slope. So they're at 100-meter elevation, each of them, and they're just dead flat. They'll get walls on the side that are automatically going to get drawn, but my profile is just dead flat. That doesn't help us much. So we want some slope to this. Manning's equation, if we want to compare it to Manning's equation, would fall apart at 0 slope, right? So I'm going to give it a longitudinal slope, not just for the energy gradient to get, but we'll also get a slope this way by adding to the elevation. We'll actually get a bed slope and a friction slope and everything being parallel so that we get some uniform flow here. So I'm going to add 4 centimeters here, because it's 40 meters long. That gives us a 0.1% slope. So in that case, then the middle one, I'm going to raise that by 2 centimeters. So I'll do that manually here. And now I've got a gradient from upstream to downstream, and I will save that geometry. Now you can see on the longitudinal slope, I've got my 0.1% moving downstream. So let's see, I'll save this as we go here, just so I don't lose anything. And then I could go in and enter steady data here. Let's go ahead and that'll be our next step. Let's keep it simple, and I'll make it 1 cubic meter a second. And let's assign the outlet to be a downstream normal depth gradient of 0.001, so 1 meter per 1,000 meters, I guess, so 1 out of 1,000, or a 0.1% slope. So I'll assign on the name, I'll give it a name that includes the flow rate and the slope, just so I make sure I keep this separate in case I make any changes later on. So 1 cubic meter a second at a 0.1% slope, and that's my steady flow. So let's see, there's one thing before I run this. I guess one thing we need to talk about is the roughness. So I haven't assigned the roughness coefficient yet in this model, and so I'll need to go back in and do that. What should we make this out of? I don't know, smooth dirt, grass, turf, astroturf, whatever they might have out there, some gravels. Let's just choose an intermediate value. So I'll need to just click on the geometry here and open up the cross sections, and I'll just do it through the table. It's got this no data value assigned to it to begin with, and we'll just make it 0.02. So the 0.02 friction, we can look up the tables and see what might be reasonable, run some sensitivities, but we'll just keep this pretty basic for now. So I can see now, if I turn these on, there are 3 different cross sections now at 3 different elevations, 3 different levels. So I'll save my geometry, exit out of that, and let's compute it and see how quickly it goes, because that's one of the things we're going to be testing today is the speed. Well, this one was less than 2 seconds by the time it ran it, so almost instantaneous. Let's look at the profile now, and you can see I've got a slope there. Now that should be parallel, but I've only got 3 cross sections, so there might be a few discrepancies in terms of how parallel that is. It's dead flat across the top. You can see that I'm below critical depth there, so this is a subcritical run. There's again critical and my water surface, and if I check the tables here, I can see that my Froude number is 0.37, and I've got water surface is about 20 centimeters deep, and we can check later on to see if that makes sense. Velocity is 0.5 meters a second. So that's my uniform rectangular channel running down. Say I'm pumping water in from the upstream end and letting it flow out the downstream end at a 1.1% slope. So there's my depth. You can see that flow profile there in the results. And now let's go ahead and do a 2D to compare. 2D terrace. So in this case, I'm going to add a grid around the same area. And for the perimeter, I could just make a shapefile out of this and use the same one that I had used to delineate my 100-meter high elevation. I'll just fudge it in here and get it as close as I can. And in this case, this becomes my 40-meter by 10-meter terrace that I'll run some flow across. So the perimeter itself is going to get the same name. I'm going to keep this as large a cell as I can just to demonstrate the purposes here. I'll make it 5 meters, match the Manning's end of 0.02, and we'll generate this. This is not going to come in, it'll come in orthogonally, but I want to make sure this is oriented in line with the same flow direction as the 1D model. And so I'm going to go ahead and just I'll put a break line down the middle of this thing, maybe just for reference. I'll use the 1D alignment here and turn them on so I can match that. So again, I'll just take a break line right down the middle, and that break line then I'll give it a, well, I can give it a name here. This is going to be the center line of my terrace, and now I want to orient everything along it. So what I'll do here is just give it a some near repeats, because near repeats will allow us to just orient in any direction that we choose instead of being orthogonal in this case, even though it looks like it's 3D. So I'll give it a few near repeats. Far spacing I'm going to keep the same, and we'll enforce that here and see how many we get. The dots, let me just remove those couple there in the middle, and so that we can get this thing lined up the same way as the cross-section alignment. So now I've got 1, 2, 3, 4, 5, 6, 7, 8 on one side, 8 on the other, 16 grids. So not necessarily a robust 2D model, but this thing should give us enough to compare to when we look at the 1D results. So our 2D flow area then, let's go ahead and associate this with the proper terrain in the background. This is now going to be the terrace terrain, not my ground floor terrain, which is what I've got as the basis for the rest of the model. This is just that 100-meter high grid. So as I scroll along there, you can see the elevations vary. So I've got varying elevations that are 4 centimeters higher on the upstream end, and this is then automatically going to use, now that I've associated it, it's going to use that one. Again, actually those were, now I need to assign control points along the outside here, and I'm going to put those in at 4 centimeters higher because I just realized I hadn't sloped this yet. So I'm going to give this a slope. Those previous elevations were even, yeah, now there we go, 2 centimeters in the middle and exactly 100 at the end. So I'm 4 centimeters higher. And so I've done this with control control points. And this way, if I open up the 2D geometry, then we'll be able to see how that has now been sloped. So that 100-meter surface is now tilted upwards with a 4 centimeter rise, so 1.1% gradient underneath it. So those cells will then be computed based on that terrain data. So now I need to add some boundary condition lines, the upstream and the downstream boundary condition lines, inflow coming in from the bottom, outflow going in out from the top right there. And if I pull this thing across, then give it a name, I'm going to assign the same slope on the upstream and the downstream side. So let me save this, and I always like to save the geometry along the way. You just never know when you might lose it. And I will save the plan as well, and the steady flows as soon as I get those in. So normal depth on the upstream side, or sorry, on the downstream side is going to be 0.001. Again, 1 out of 1,000. And then same on the upstream end. I'm going to bring in now the 1 cubic meter a second all the way down. This shouldn't take long. I mean, how long does water take to go 40 meters? I don't need to go out to 5 hours, but I'll just put those numbers in case I do extend things later on. So I'll save that unsteady flow data. Let me just give it a name here. This is going to be, again, 1 cubic meter a second. And this is now unsteady. So I've got to run an unsteady. I don't have the option in 2D of running a steady flow. And so now I've got an unsteady 2D run to compare my 1D steady flow results to. So I don't need the post-pro. I'll just put all these on for the sake of consistency with the others, and I'll make this my 2D terrace. And we'll put this flow in. I'll just copy this across to the short ID, and we will run this one. I'd like to put these in the future after my retirement, so I know it's a hypothetical event, and we'll just run this for 2 hours, much longer than we need to run it for. So what's going to happen here if I save this and well, let's see, 1 minute. That's if we think about our Courant criteria, that's going to be quite long, and so this thing might blow up on me. Yep, let's look at that. 147% error. Yes, that was way too long for a 5-meter grid. I can't go with 1 minute, so let's go ahead and change that. Thinking about how far it might go, how fast is this going, 0.5 meter a second. We'll give it a Courant number of less than 1 here, and just allow it to move from one grid to the other, and see if that makes a difference. I'll change my output a bit so I can actually see this thing cycle through as well, and we'll save that and compute it. And now we've got a run that hopefully has got, yep, smaller mass balance error. So it's pretty much negligible on the mass balance. So now I've got 2 sets of results that I can compare, and these results are going to, they're based on this 2D model. It's not great. It's got, 16 grids. How many 2D models have we ever built that only have 16 grids? But we'll see that as it's cutting these sections for a rectangular uniform channel, it's going to be just fine. So here's my my flow paths, my particle tracing. You can see it running from one end to the other. Again, a bit gimmicky in this case, but it does show us the flow directions. So I should have called this 1 cubic meter a second. So I'll go ahead and rename that in a bit here. But let's try running it. That was diffusion wave, the simplification, and just to prove to ourselves that it doesn't make a difference. My depths were 19 centimeters before. I'm going to run this now as a full momentum, the shallow water equation, and let's see what we get here. We got a little bit bigger mass balance error, but now when I check the results, let me turn off the particle tracing, and it's still 19 centimeters deep. Same thing. It didn't make a bit of difference whether we ran at full momentum or diffusion wave. And likewise on the velocities, those are going to be consistent at 0.53 as well. Oh, for the 1D, let me go in and check, and we'll just go back and compare that to the table, and you can see, oh, the velocity is 0.53 instead of 0.52. You can see how the depth's changing a little bit there. If I inserted more sections, that'd be the same. Let me just type this into, I've got these values that I already chucked into an online Manning's calculator, and you can see with 1.0000 discharge in my Q and the same channel slopes, I get 0.19374. So that just shows us that we're matching. The velocity, yeah, 0.52. So we are right on. How well do we ever know, things to 1% or less? That's probably more accuracy than we're likely to find anywhere else. And again, there's going to be more uncertainty in our Manning's roughness. So let's go ahead and now change this 1D to an unsteady. So I'm going to go ahead and save the unsteady data here. Instead of 2D, this is now going to be 1D. And let's see if our steady flow and unsteady flow give us any differences. So I'm going to give exactly the same boundary conditions as I had for my 2D model. And now I've got 0 at the downstream end. I'll give it the normal depth, again 0.001. And that's 1 in 1,000. And then at the upstream end, I'm going to give it the same thing, the flow hydrograph. What if we wanted to ramp this up? I think we've talked before about how flows need to ramp up gradually in HEC-RAS. It doesn't like to just start with a massive amount of flow. Well, what would happen if we just ramped it from 0? I'm going to save this one and also save the plan. This is going to be a 1D model with unsteady flow. And I'll put that in the short ID as well. And then we'll have this one saved. I'll turn on all the same features here and try to make it similar in the run the simulation window. So going 2 hours worth. Technically, I should apply the Courant number criteria to the cross-section spacing as well. In this case, I've only got 3 cross-sections, so I can go a little bit farther, right? They're farther apart than the grids were. I'm going to go with 10 seconds then. So I've got, I'll go back to 5 minutes for all of these like I did in the 2D one, and we'll keep it at that and save the plan. So with that plan saved, I've now got my flow hydrograph in there. What do you think is going to happen? If we hit run, remember it's ramping up from 0, we're not going to get any results at all. Why not? Well, we could have changed, between finite difference and finite volume and been able to account for that 0 flow. But in our case, the way we're running it, we cannot have 0 flow. So you can either change it there and can assign a minimum flow. You could also instead, even if you had some flows going below it in the beginning, we could assign an initial flow here. Wherever you want to assign that, we just need to override the 0. We can't have a 0 flow in this case. And so when I now hit run and hit compute, I should hopefully get some results here that are going to be a bit more reasonable than 3 seconds. So it took a little bit longer than the steady flow, but only by a second or so. So let's have a look at these results. Let's pull RAS Mapper back up here, and we've got unsteady results and we've got steady results. And if we have a look there, now here's my 1D unsteady. Look at that, exactly the same, 0.19. What do you know? Well, but velocities, I think there might have been some instabilities in there. So let's go back on the velocity table, because it's going to track all of your any instabilities you might have had along the way at any computational interval, not just the output intervals. But let's go ahead there and have a look then at the table and see if we can get those results for the 1D unsteady. Yep, it's the same. So you can see it's actually matching exactly the same for my water surface elevations as the steady run. So I've got these 3 runs, steady and unsteady for 1D. 2D I can't run as steady, so I've just got the 2D shown this way. Let me just save everything and go back to my results here, and then we can maybe plot a profile of this and see if we can compare our water surface elevations. Again, there's my particle tracing, just showing the direction that it's going in. I'm going to plot this. Usually I like to just grab my center lines off of a shapefile and import those so that they line up exactly. In this case, I'll just fudge it in again and go right down the center line of the terrace as a profile. So when I do that, I'll go ahead and make sure I'm turning on my maximum water surface elevations. I can check each of these 3, and when I plot them out, you can see there's a little bit of a difference. Is that because I had such a wide grid spacing and cross-section spacing? Well, you look at those axes there, that's, each of those grids is 1 millimeter. The fine grids there is 1 millimeter apart. So it's still pretty close. There may be some conceptual differences in how these are handled. You can see it's actually a bit closer right at the end. So just to check ourselves, let's see what happens if I take the 2D and maybe the full momentum versus diffusion wave. Let's go ahead and save that one again. I didn't save it last time, just right over the top. So I'm going to change this back to diffusion wave and call it DW. So with this one called DW, I'll save this plan and run it, and now we'll have an extra profile to compare. And let's see, is there a bigger difference between 1D and 2D, or between 2D in diffusion wave and full momentum mode? Well, let's have a look here. I'll close that out and add that to the profiles, and what you'll see here is that my two 2D ones, I think, because it's uniform, shouldn't be much difference at all. Okay, it's not even a millimeter, so it's well within the accuracy of the model here, the reliability of the model results. So with that, let's go back again and just look at the geometry. Maybe the grid size, maybe refining the grid size. Did we get to convergence here? Would we get to convergence if we change this, say, to a 1 meter grid instead? And I could do the same with cross sections. I'll pop those results in later if I can generate some interpolated cross sections. But right at this point, let's just go in and just change the grid to 1 meter. Now with the grid at 1 meter, again, that's going to be 5 by 5 meter ahead there. So that's 25 cells for every one we had before. So we've got 25 times more grids. And so with that 1 meter grid, you can see those ones. Let's see, I'll turn off that one and turn on the break lines here. And what I'll do is use that same break line, and to get them oriented in the same way, I'm just going to change it to 1 here, and now I'm going to need some extra repeats. So a 1 meter near spacing, and I'm going to repeat it at least 5 times, and that way on both sides of it I'll have 5 1 meter grids. And that should, if I go in and enforce this one, hopefully they'll line up with my center line. There they are. So there's my 1 meter grids. So I'll save that. And it's still not going to run for very long because it's still a very small model, but it will take a little bit longer to run this same model here. And let's just see what happens if I even take this down and let HEC-RAS adjust the time step here. And let's assume it's explicit and has to be below 1 as the Courant number. That'll give us our most stable results here. And as I run this thing, let's see how much longer it takes. Yeah, a few extra seconds. So again, not a whole lot of grids in this one, but as I load this in and have a look at the results, let's see, did it help us? Did we get to some sort of convergence? So I'll go back and turn this new one on. Right click on this and hit my water surface elevation. Okay, so what made a bigger difference? Well, there you can see the two 2D results and then the two 1D results up above that. So, maybe I got more accurate with the 1 meter spacing, but in the end, what you can see is the 1D results use exactly the same, steady or unsteady, has exactly the same boundary condition. Likewise, the 2D to the millimeter is exactly the same at the boundary condition. It doesn't begin to diverge until after that. And if you look at these results here, 19374, it's right in between the 1D and the 2D results. So that's I've done the same on some of these ones where I took the cross section spacing in the 1D and interpolated those, and it actually makes a smaller difference than anything else. They end up right up on top of each other as well. So upstream there's about a 1 millimeter difference if I try this with interpolated cross sections. So let me zoom back out on that. This was our Empire State Building tutorial. You could do this with any classroom on the planet. This is what we do, and then I can kind of walk around and see that and see what's going on. So that's when we're looking at a uniform mild gradient channel, the approach we take shouldn't really matter. Now that we have the model all set up, we should be able to test out all the different principles and the sensitivities and parameters that we're covering in this course. If you want to put any questions into the chat line or submit them through the learning platform, we'll bring our other presenters back on for a discussion before moving ahead to the next topic. So we'll close it there.